Hello class, welcome to Connected. In this chapter, we will learn about elements, laws given by different scientists, periodic table and their values and sizes. In class 9, we have discovered that matter around us is available in the structure of components, mixtures and combinations, and the components contain atoms of just one type. Do you realize what numbers of components are known till date? As of now, 118 components are known to us. All these have unique properties. Out of these 118, just 94 are natural happening. As various components were being found, researchers assembled furthermore and more data about the properties of these components were collected. They found it hard to put together all that was thought about the components. They began searching for some example in their properties based on which they could concentrate countless components. Many things are classified into various categories according to their properties. For example, in a shop, soaps are kept together at one place while biscuits are kept together at another place. Even among soaps, bathing soaps are stacked separately from washing soaps. Similarly, scientists made several attempts to classify elements according to their properties and obtain an orderly arrangement out of mess. The attempts to classify the elements resulted in grouping the known elements as metals and non-metals. Later, they were more classified according to knowledge of elements and their properties, which were increased in future. Dobereiner Triads. In the year 1817, Johann Wolfgang Dobereiner, a German chemist, tried to arrange the elements with similar properties into groups. He identified some groups having 3 elements each, so he called these groups triads. Dobereiner showed that when the elements in a triad were written in the order of increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. For example, take the triad consisting of lithium Li, sodium Na and potassium K with the respective atomic masses 6.9, 23 and 39. These elements are arranged downwards in order of increasing atomic masses. You will find that groups B and C form Dobereiner triads. Dobereiner could identify only 3 triads from the elements known at that time. Hence, this system of classification into triads was not found to be useful. After this scientist, many other scientists also started working and correlated elements with their atomic numbers. Newland's law of octaves. In 1866, John Newland, an English scientist, arranged the then known elements in the order of increasing atomic masses. He started with the element having the lowest atomic mass, hydrogen, and ended at thorium, which was the 56th element. He found that every 8th element had properties similar to that of the first. He compares this to the octaves found in music. Therefore, he called it the law of octaves. It is known as Newland's law of octaves. In Newland's octaves, the properties of lithium and sodium were found to be the same. Sodium is the 8th element after lithium. Similarly, beryllium and magnesium resemble each other. A part of the original form of Newland's octaves is given in table. It was found that the law of octaves was applicable only up to calcium, as after calcium, every 8th element did not possess properties similar to that of the first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in the future. But later on, several new elements were discovered whose properties did not fit into the law of octaves. In order to fit elements into his table, Newlands adjusted 2 elements in the same slot, but also put some unlike elements under the same note. We can see that cobalt and nickel are in the same slot and these are placed in the same column as fluorine, chlorine and bromine, which have very different properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. With the discovery of noble gases, the law of octaves became irrelevant. Thus, Newland's law of octaves worked well with lighter elements only. Making order out of chaos. Mendeleev's periodic table. Even after rejection of many scientists, some still continued their research on the elements and their properties. And the main credit for classifying elements goes to Dmitry Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the early development of a periodic table of elements wherein the elements were arranged on the basis of their fundamental property, the atomic mass, and also on the similarity of chemical properties. At the point when Mendeleev began his work, 63 components were known. He analyzed the connection between the atomic masses of the components and their physical and chemical properties. Among chemical properties, Mendeleev focused on the mixtures formed by components with oxygen and hydrogen. He chose hydrogen and oxygen as they are extremely reactive and mixed with most components. The formulae of the hydrides and oxides framed by a component were treated as one of the fundamental properties of a component for its grouping. He at that point took 63 cards, and on each card he recorded the properties of one component. He figured out the components with comparative properties and stuck the cards together on a divider. He saw that a large portion of the components got a spot in a periodic table and were organized in their increasing order. On this premise, Mendeleev detailed a periodic law which says that the properties of elements are the periodic function of their atomic masses. Mendeleev's periodic table contains vertical columns called groups and horizontal rows called periods. Mendeleev's periodic table was published in a German journal in 1872. In the formula for oxides and hydrides, at the top of the columns, the letter R is used to represent any of the elements in the group. Note the way formulae are written. For example, the hydride of carbon, CH4, is written as RH4 and the oxide CO2 as RO2. Achievements of Mendeleev's periodic table. While developing the periodic table, there were a couple of occasions where Mendeleev needed to put a component with a marginally more prominent atomic mass before a component with a marginally lower atomic mass. The grouping was altered so components with comparative properties could be gathered together. For example, cobalt, atomic mass 58.9, appeared before nickel, atomic mass 58.7. Further, Mendeleev left some gaps in his periodic table. Instead of looking upon these gaps as defects, Mendeleev boldly predicted the existence of some elements that had not been discovered at that time. Mendeleev named them by prefixing a Sanskrit numeral Ika. This gave persuading proof to both the accuracy and convenience of Mendeleev's periodic table. Further, it was the remarkable achievement of Mendeleev's forecast that drove scientists not just to acknowledge his periodic table, yet in addition, remember him as the originator of the idea on which it is based. Respectable gases like helium, He, neon, Ne, and argon, Ar, have been referenced in numerous a setting before this. These gases were found late in light of the fact that they are inert and present in very low fixations in our air. One of the qualities of Mendeleev's periodic table was that these gases were found. They could be set in another gathering without upsetting the existing request. Limitations of Mendeleev's classification. Electronic configuration of hydrogen resembles that of alkali metals. Like alkali metals, hydrogen combines with halogens, oxygen, and sulfur to form compounds having similar formulae. On the other hand, just like halogens, hydrogen also exists as diatomic molecules, and it combines with metals and nonmetals to form covalent compounds. Positively, no fixed position can be given to hydrogen in the periodic table. This was the main impediment of Mendeleev's periodic table. He couldn't allocate a right position to hydrogen in his table. Isotopes were found long after Mendeleev had proposed his occasional arrangement of components. Allow us to review those isotopes of a component having comparative compound properties yet unique nuclear masses. Thus, isotopes of all elements posed a challenge to Mendeleev's periodic law. Another problem was that the atomic masses do not increase in a regular manner in going from one element to the next. So, it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements. Making order out of chaos, the modern periodic table. In 1913, Henry Moseley showed that the atomic number, symbolized as Z, of an element is a more fundamental property than its atomic mass. Accordingly, Mendeleev's periodic law was modified and atomic number was adopted as the basis of modern periodic table. The modern periodic law can be stated as follows. Properties of elements are a periodic function of their atomic number. Let us recall that the atomic number gives us the number of protons in the nucleus of an atom, and this number increases by 1 in going from one element to the next. Elements, when arranged in order of increasing atomic number, lead us to the classification known as the modern periodic table. Prediction of properties of elements could be made with more precision when elements were arranged on the basis of increasing atomic number. Position of elements in the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. The placement of elements are decided as per the number of valence electrons that are present in the outermost cell. For example, fluorine and chlorine have same number of valence electrons, that is 7, so they are in the group 17. Hence, we can say that groups in the periodic table signify an identical outer shell electronic configuration. On the other hand, the number of shells increases as we go down the group. Trends in the modern periodic table. Valency. The valency of an element is determined by the number of valence electrons present in the outermost shell of its atom. Atomic size. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. The atomic radius of hydrogen atom is 37 pm, picometer. 1 pm equals to 10 to 12 m. The atomic radius decreases in moving from left to right along a period. This is due to an increase in nuclear charge, which tends to pull the electrons closer to the nucleus and reduces the size of the atom. The atomic size increases down the group. This is because new shells are being added as we go down the group. This increases the distance between the outermost electrons and the nucleus so that the atomic size increases in spite of the increase in nuclear charge. Metallic and non-metallic properties. The metals like Na and Mg are towards the left-hand side of the periodic table, while the non-metals like sulfur and chlorine are found on the right-hand side. In the middle, we have silicon, which is classified as a semi-metal or metalloid because it exhibits some properties of both metals and non-metals. In the modern periodic table, a zigzag line separates metals from non-metals. The borderline elements boron, silicon, germanium, arsenic, antimony, tellurium, and polonium are intermediate in properties and are called metalloids or semi-metals. As the effective nuclear charge acting on the valence shell electrons increases across a period, the tendency to lose electrons will decrease. Down the group, the effective nuclear charge experienced by valence electrons is decreasing because the outermost electrons are farther away from the nucleus. Therefore, these can be lost easily. Hence, metallic character decreases across a period and increases down a group. Non-metals, on the other hand, are electronegative. They tend to form bonds by gaining electrons. As the trends in the electronegativity show, non-metals are found on the right-hand side of the periodic table towards the top. These trends also help us to predict the nature of oxides formed by the elements because it is known to you that the oxides of metals are basic and that of non-metals are acidic in general. Now, let's discuss some questions and answers. Question: what is Newland's law of octaves? Answer: The Newland's law of octaves states that every eighth element has properties similar to that of the first when the elements are arranged in the increasing order of their atomic masses. Question: what was the basis of Mendeleev's classification of elements? Mendeleev's periodic table is based on the fact that the physical and chemical properties of elements are a periodic function of their atomic masses. It means that when the elements are arranged in order of increasing atomic masses, the elements with similar properties recur at regular intervals. Question: which two observations in Mendeleev's periodic table posed a challenge to his periodic law? Answer: the following observations posed a challenge to Mendeleev's periodic law. Increasing order of atomic weights could not be maintained while arranging elements with similar chemical properties. Chemical properties do not depend upon atomic mass. Isotopes of all elements have different atomic mass but same chemical properties. Question: what do we call the elements having properties intermediate in between metals and non-metals? Answer: metalloids. Question: why do all the elements in a group of the modern periodic table have similar chemical properties? Answer: all the elements of a group of the modern periodic table have similar chemical properties because they have the same number of valence electrons in the outermost shell. Question: define modern periodic table. Answer: modern periodic law states that properties of elements are a periodic function of their atomic number. So that's it for today, class. We have completed chapter 5. Thank you and hope you all had fun learning.